All right. Okay, I'm live now. Let me see. Dreamer, dreamer, dreamer. Okay, this is good. Um, yeah. So, for the past week, I have been studying stacks. Just been doing basic problems, and today I would like to try something different. Upgrade it a little and see what upgrade the difficulty of the questions I solve in terms of stacks. Maybe not upgrading per se, but like just solving more questions within a given time. And according to, so these are, I've not studied recursion, but I sort of know what recursion is. It's a function calling itself. Uh, but I'll see this one, and then there are other medium questions to hard questions. Well, the best place to get questions will be Leet Code. I'll just go to Leet Code instead. Sorry, I don't know why my caps is on. Let's go to Leet Code. Sorry. So I'll just go to Leet Code. Leet Code instead to get my questions. Let me just rest my hand properly. Alright, so we have Leet Code here. I'll come to this place. What? I'm not. I'll just go to the explore page. Sorry, explore. Oh, so problems. Yeah, yeah, problems. And I would like to target stacks. So where is stacks here? Yeah, this is stack. We have about 115 questions. I've solved 4 stacked problems so far. I did valid parenthesis yesterday. I also did some other min stack. Did I do min stack is medium question? Wow, interesting. Evaluate. You know what? I want to solve. This is hard. I'll try solving um, some medium questions first. It will never go. So, well, okay. So these are the medium questions. I'll. This is 21%. Wow. Steps to make an array non-decreasing. Try it out. Check if a parenthesis string can be valid. Okay, I'll take this one. I'll start from that since I did something similar yesterday. Remove k digits. This will be interesting too. So let's start with this one here I've solved before. Um, okay, so I'll just close that. And the question is simple, and I remember this question very well. Um, so what the question is asking is to okay, so design a stack that supports push, pop, top, and retrieving the minimum element at constant time. Okay, retrieving the minimum element at constant time. Implement min stack class. So min stack class initializes the stack objects. Okay. Um, void, right? This will return. So push is just a function that adds a value to the stack, pushes the element value onto the stack. Pop removes. Void is just what the function returns. It means the function is not returning anything, right? So pop method removes an element, removes the element from on top of the stack. Sorry, on top of the stack. Top gets the top element of the stack, and getMin retrieves the minimum element in the stack. You must implement a solution with O of 1 time complexity for each function. Each function has to do specifically just one thing, and not, which means you cannot run like multiple loops in a function, like in each of these methods. So this is the name of our, yeah, this is quite simple, right? Although it's a medium question. Well, I remember solving this question, and it was just one thing that I couldn't get right, but the rest were just implementing the stack. So this is quite straightforward. I'll just go ahead and implement this. I'll just say new file. The main stack here. This is the main stack, and here's what I'm going to do. Well, I usually explain the question first, so let me go ahead and try to explain the question and understand what is needed. But this doesn't really have like any explanation aside from one key point to note, which is the retrieval of the minimum element in the stack. Aside this, these are just normal functions that will look into our stack. So we'll have a class, and we initiate a property of the class, which is going to be our stack. And then every time we can push an item to the stack, we can pop an item from the top of the stack. We can look at the top of the stack and see which item has the highest value, right? We can look at the top of the stack to get the item that is on top of the stack, or the item which is on top of the stack. Then getMin, right? getMinimum retrieves the minimum element in the stack. This is so important, right? So how do we do this? Well, to be able to get the minimum value, we need to store the minimum value somewhere, right? Because we want to also get that at constant time, which means we can have like we can have like a, so every time we push an item into the stack, right? We want to check if there is an item already in the stack, and then in the case where there is not, the first item that goes into the stack, right, will be the current minimum that we have, because there was no any other item in the stack. So we can store that minimum somewhere, right? And every time we add an item onto the stack, we want to compare it against the minimum we stored before or previously. And when the current item, that is being introduced into the stack, when that item is smaller than the minimum we had previously, then it becomes the minimum. But there's a catch for that, right? There's a catch for that. In the case where the current item we added to the stack is being removed, it means we also have to remove that item as the minimum item, right? And in this case, that means we will not have any minimum. We will not have any minimum, and that will probably not work that way. When we pop an item from the stack, right, that is also a minimum, we want to remove it as the minimum, which means any other value before it has to be has to become the minimum, which means we'll have two stacks, right? Two stacks for the minimum value. So here's what I'm going to do. I'm just going to come here. Sorry. I'm just going to come here and I'll set this as my values, right? So here I have, let me go this way. So here I have um, an array, right, which represents my, let me just write some numbers here. Where is the question? So I'm just going to use this 2 1 blah 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 minus 3. So here's what I'm going to do. Here's what I'm going to do. I'll just minus 2, right? So I'll start from -2, let's say -2 5. We are pushing this, right, onto the stack. So we'll have an array like this, and then okay, let's do it this way. I'm just going to start like this. I have my stack here, and I add -2 to the stack, right? -2, right? I'll just put this minimum here, right, is equal to -2 because there was no item in the stack at this point, right? Now when I add 5, right, when I add 5, well, since it's a stack, we want to be able to retrieve the element the element that is the, you know, the minimum in this stack here in constant time. So here we've already added -2. Is -2 less than 5? No, so we don't add 5 onto this stack here. We don't add 5 here. The next time we see an item, I'll say maybe -1. Yeah, -1 is also bigger than -2, so we don't add it to the stack, right? And then when we have like -3, right, -3 next, then we can add -3 to our stack like this, right? So when we pop -3 from the stack, we also want to pop this -3 from here, okay? And then when we pop this -1, we also have to check if its value is here. If it's not, then we don't do any pop from here. The current minimum in this stack here will still be 2, unless we pop 2 and 2 is inside this minimum value. Then we can, we can empty the stack. Yeah, I think that works. So here's my implementation. So I'll need to code this out myself, but I'll need the boilerplate code. So let me just open this. This is, so you can see we have a minimum array here, which also acts like a stack, right? And then every time we push to this thing, we want to compare the value of the previous one. If it's the minimum value, then we set it as our current minimum, right? We add it to the stack. Otherwise, if it's not, so this value takes mean. This is a built-in function, mean value, right? This value is just the current value in this stack here, right, that we are looking at. So we want to look at the stack. We want to find the minimum value, self min -1. So this will get the last item in the minimum array, right? Actually, the reason why we don't need to loop through the stack is because we are adding and retrieving at constant time. So retrieval has to be constant and adding also has to be constant time. So here you go. We add an item to the stack. We also want to find out if that current item is the current minimum. We could have negative 2 in the stack and then at some point decide to add negative 3. Negative 3 is smaller than negative 2, right? So we want to add negative 2 as our negative 3 as our current minimum instead of negative 2, which was the minimum previously. So, and yeah, when we find a minimum, we always want to append a minimum. And when we remove the value, right, we also want to remove one from the minimum, like I said here. So why do we do this, right? We want to keep the current minimum up to date. So mm, this this is good. So here is how you can pop. After popping from the stack, you also want to pop um, from the minimum stack. But here I was wondering, oh god, they've taken the lights. I don't know what to do again at this point. This is so disappointing. Oh my god. Please let there be light. My light has gone. Ugh. Completely paralyzed. They've brought it back again. I hope this stream did not end. Otherwise I'll be really, really pissed. Um okay. Um Honestly, that was disappointing. But yeah, we are back. So here's how I implemented the minimum value from the stack. But I kind of have like a problem with this implementation, right? So here is what, well, mean this built-in function returns self-domain. Okay, so an item of the stack. Here, this function says the main function in Python determines the minimum between two values. So self-domain minus 1, if self-domain, if there's an item, otherwise use the value. Yeah, so it will return the minimum value here, just like in in max built-in function. Ah, this is interesting. I'm battling everything. Network, light, everything. This is crazy. I'm just hoping this works very well. Okay. Oh, I don't know. I don't know. I decided to record this early so that, you know, I don't face the issue of light outage. But yeah, here we are. So, what I was saying here is, I think this is wrong, given the fact that we are removing the current minimum in the item, in the minimum stack or minimum array, right? So, the reason why I think this could be cause an issue is, let's say for instance we added a minimum value to the stack, right? Like this. So I'll, go over this and remove this. Yeah, so we have like -2, we add -2 to the stack, -3, -1, we have 6 and so on, right? If we added, the current item to the stack, right? Because this one is the um I'll call this min stack, right? This item here is our current item and we don't have any other item in the stack yet, so no comparison needed. We just add it to the stack, so we consider this our current minimum. The next item is -3, but when we compare -3 with -2, right, -2 is smaller, right? So we want to add -2 on top of our stack. So -3 at the top of our stack, right? We calculate, we see the next item here is -1. -1 is not bigger than -3. I mean, -3 is, 1 is superior to -3. So we don't add this to the stack, we skip, right? And then so on, we get to this point, we also skip, the fact that this is, we don't skip, we move to the next one. Sorry, we move from here to here, and then we are now at this position here, but we can't add this to the stack as well because -6, I mean 6 is bigger than -3, right? So when we pop an item from this stack, what this implementation says is, when we pop an item, from the stack, right, this, the topmost item here should also be removed, which is not um which is not correct, because when we are popping 6, why are we removing 3 from our minimum stack, right? Because 3 is still in the stack here, and 3 has to always be in the minimum stack. We want the minimum in a particular stack, right? So we can't just remove, we want the minimum value in the stack, so we can't just remove 3. So we need to find out if the current element that we are removing is actually in the stack. If the element is All right. Sorry about that. Okay, so what I was saying here is when we pop an item from this stack, we're also removing from the top of the minimum minimum array that we have here, right? The minimum array contains minimum items in the stack. So we only need to pop from the stack when we are removing a particular item that matches the minimum, right? So this 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 here has to be improved, right? This here has to be improved because it doesn't it does to me. I still need to know. Yeah, we are getting the last item from the minimum array here. So when we are popping, we also need to know if the last item we are popping from the stack is equal to the last item that was added at the top of the. I mean, we need to know if the item at the top of the stack that is being popped or removed is also the same as the current item we have at the top of our main stack. Yeah, because we are not just appending to the main stack, we are appending based on a certain value. So if there's an item in the main stack, right, if there's an item in the main stack, then we want to use that item, the last item at the top of the main stack. Otherwise we just use the value as the current minimum. So here's what I need to do. I need to improve this. So I'll say remove, right? But if if self dot stack, right, self dot stack, the last item here, right, is the same as self. I mean, this might not cause a problem, but self don't mean the last item there. Then we want to do this. We want to do this. Yeah. Oh, okay. So after popping, this will. Oh, I see. After popping, the last item in the array will not be this. Well, when we pop, right, when I get the value to know, like here now, let's say when I have an array, I'll just do this. Where's my playground? Yeah, so here's my playground. I have an array. I'll call this. Um, I'll just call the stack is equal to an array of numbers, right? 2, 5, 6. This is enough. And then let's just say egg. Okay, popped. I'll just call this popped, right? Sorry. I'll call this popped and say this is equal to stack dot pop, right? So we remove, and then I'll print both stack and popped, and then stack. Sorry. Oh, print popped and stack. So here, let's run this. If it changes, that's good, right? So popped, of course we popped for okay. So the value of stack, good. This is okay. I see. So unless the item we are popping from our stack is actually, what is the current minimum, then we don't remove the minimum from the stack yet. So here's what we're going to do. I'll say yeah, I've just got this popped, right? Okay, popped is equal to this, And then if popped here, right, if popped is this, then we want to remove this as our minimum. I think this should work. Yeah, it worked, right? It worked, but I don't think they were even accounting for that. You know, in extreme cases like this where we are just removing without adding, right? So let's submit this and see if it works. Oh, oh, wrong answer. Yeah, I think they were not accounting for that. They weren't. Min stack push push push. So when we do min stack push, we find out if the current item that we're pushing in the into onto our stack is the minimum we have. If it is, then we add it. We find push again, push push push. So let's see. Um, what are we even pushing here? So this is where the issue is. Output is this. It's supposed to be 0. It's supposed to be 2. When we are removing from the stack, right? Yeah, it's logical that we know, you know, which item is being removed. It could be that we are removing the minimum value that we currently have in our stack, and if that is being removed from the stack, then it's no longer the minimum value in the stack, right? I mean, unless we know that, you know, every time we add an item to the stack, then it is the minimum, right? It is the minimum as well. Cause here, right, if use the last item to compare if there's an item in the stack, otherwise use this value and compare to the previous value. But this val here is not really anything. This is interesting. I want to know why this works. So when I do this and submit this, this will work, right? But this is not even accounting for that edge case where I'm looking at the current item that is being removed. So let me just illustrate this a bit. I think there's an issue with this. Maybe I'm overthinking it, but so I'll follow these steps. I'll just put this on the window and then, you know, just remove this from here. So first of all, in the test case, right, um, I'll just come here. So here's the test they had this test here. So we started from min stack, we pushed onto min stack, we pushed 3 times. So just a minute. So here's, we created new stack, we pushed negative 2 to the stack. So negative 2 will be our current minimum automatically. 0 is bigger than negative 2, right? So negative 2 remains our current minimum. So we did all our push, right? We did every push that we wanted to do. Oh, okay. Well, you see, the get min here is negative 3. Hold on. Negative 3. So every time we push an item onto the stack, doesn't mean we are pushing in a certain order. Hold, I don't. Hold on. I think I'm over. I'm not thinking straight. Um, we push negative 2 onto the stack. We push 0 onto the stack. Well, we compare 0 to negative 2 if they are not this, if 0 is not the minimum here, we keep negative 2 on top of our minimum array, right? Or minimum stack. I'll just call this min stack, although the class name is min stack, right? So what really happens here is, uh, okay, so somebody is asking in the chat, what are you creating? I'm not creating anything, I'm solving late code problems. So it's like technical coding problems. Yeah. So if when we keep negative 2 as our current minimum, so we only add to the stack anytime we have a minimum, right? Anytime we add to this minimum stack here, we only add to this minimum stack anytime we actually have a minimum. Otherwise, when the value is bigger, then we don't add it to the stack. Yes, that's logical and makes sense. But when we remove an item from the stack, right, it means we are removing the topmost item from the stack, regardless of the order in which. So let me just do this again. So we have negative. I'll represent this our stack like this. So, oh my god, this is not what I want. So here is going to be our main stack, and then here is just going to be the um I'll just put class stack here, class stack, right? Then we have our numbers. Our The first item we are adding to the stack is negative 2, right? We start from negative 2. So negative 2 is here, right? And then the current minimum in this min stack here, there is no value here. So since it's the first one, we just add it to the minimum stack. Then the next time we want to add 0 to the stack, so we add 0 correctly, no problem. So 0 is there. The next item, that goes into this minimum stack would have been 0 if 0 was less than negative 2. But 0 is bigger than negative 2, so we don't add 0 here. So 0 is out. The next item we want to add here is negative 3, right? Oh my god, my 3 is not nice. So negative 3 like that. So negative 3 is added to the stack, right? So we have negative 3 here. Is negative 3 bigger or smaller than negative 2? Negative 3 is smaller. So we put negative 3 on top of negative 2. So negative 3 becomes our current minimum at this point, right? So here's what I was saying. Now, when we want to pop an item off the stack, we also want to look into the stack and see the current minimum so that we know which one is left, right? So here's what we do. Um, we remove negative 3 from the stack, we pop negative 3. Let's just cancel it like this. Then we have to look into the minimum stack, because when we look at the stack right now, right, from 0, negative 2 to 0, negative 2 is the minimum stack, the minimum item in this stack here. And if we look into our minimum stack, we always want the topmost item to be our current minimum, right? So the item at the top. But because we are removing negative 3 from our original stack, we also want to remove negative 3 from the minimum stack, so that we keep a constant time lookup for any minimum in the stack. Otherwise, we'll have to, loop through this stack here and compare each time to find which one is the minimum. But because we know we are storing minimum items in the min stack here, then the topmost item will be the minimum. So we remove negative 3 here, right? Then we still have 0 and negative 2. But to get the minimum item, we just need to look at the top. What's at the top of this min stack here? It is negative 2, because we already removed negative 3. So negative 2 is our current minimum. When we remove 0, right? When we remove 0, what happens then? Do we remove negative 2 as well, because we are removing an item from the stack? No, we won't do that, right? So, which is where I had a problem with my previous implementation, right? Where is it? Okay, here. Let me drag it back. So here I'm saying pop an item off the stack, right? Sorry. I still left this here. Okay. Remove an item from the stack and remove an item from the minimum stack as well. This doesn't really make sense to me. It doesn't really make sense to me, because I only want to remove an item from the stack if that item is at the top of the minimum stack. Otherwise, I don't, right? I just keep it there. Just like this case here, where 0 is the item I want to remove from this stack here. I don't need to remove negative 2, because negative 2 still remains in our stack. Our stack will still look like this at the end of the day, right? Negative 2, because we removed 0, right? And negative 2 still appear there. Unless I'm removing negative 2, then I can remove negative 2 from our minimum stack. Actually, that's how I understood the question. But yeah, I think that edge case should actually be there. Otherwise, there's something else going on. And let's see. Let me just go back, copy this, and I will need to test with every possible case I have. So min stack here, right? I will create an instance of the so I'll just call this solution and set to min stack. What's the name? Min stack here. And we'll do this. I will just say print. So don't worry, I can just do solution dot push negative 2 solution dot push negative 0 solution dot push. Hold on, let me just close this. I don't know why I have it here. Yeah, the push negative 3, right? And let's print this. So print solution dot stack, right? Do we have it? Okay, so it's property of the, yes. So let's print the stack. I can see we have -2, 0, and -3. Good. Now I'll start popping from the stack. So solution dot pop, right? When I pop, I remove 3 from the stack, right? And our current you know, so I'll just do like this. Print min stack, print solution dot min. I'll just put that min, right? So min should look like this. Min should only have -2 in it, right? But it has -2 and -2. Why is that? Why is this happening? Well, the reason why it's happening is because of this case here. I know why. So here we are appending onto the stack, right? Onto the min stack without even checking for a particular condition. Which is why every time we pop for an item from the stack, we also have to pop 1 from the stack. Otherwise, when we have, without popping, let me just keep everything and show the minimum stacking. Yeah, so we have negative. Yeah, I see. So here is what we need to correct here. If the current so we are comparing the value that we add in, right? Find the minimum in this. Can we do this? Yeah, we still need a subdomain -1. This can work, right? So let's say, okay, -1 is that means there's no item in this stack yet. So let's do it this way. I want to do it such that the item we are popping from the stack is it's the only item that matches the minimum item at the top of our main stack. So I'll say so append value here. Want to append this value, and then want to check if min stack, right? If there's an item, if there's min, oh sorry, self dot min. Okay, self dot min, and if there's an item there, then we want to do this. We want to take this here, right? I'll just push this forward. Okay, what have I done? Okay, and then I don't need this here. Else, if there's no item, just do self domain dot add. So I'll just copy this. Okay, self dot min dot append value, self min dot append the value. So I can now run this. Now this is still adding the minimum. Okay, interesting. Well, what if I don't want to do it this way? Right? What if I don't want to do it this way? I really want to keep values that are actually minimum and don't repeat them twice. So if self domain, right, if there's an item in the main, and then and and um and the current value we have is less than the minimum value. So self domain, right, -1, then well, we want to append here. So how this work? Wait, so 0 is not supposed to be here. Hold on. Oh, okay. Is this end here that is making it, you know? Yeah, I know why. So this won't work like this. I'm just going to copy. Let's go back again. Um, if self domain, and then if I just want to make it simple as possible, easy to. So if the value is less than mean, then do this, right? Otherwise, don't do anything. So yes, you can see we have -2 and -3 here. Okay, so the next thing to do is to respect this case here and only pop an item if the item is actually, I'll call this popped. I'll call this popped here. I set it to be equal to this. So if the popped, if popped here is the same as self domain -1, and then we want to pop the item off the stack, of the minimum stack, so it's no longer the minimum. Otherwise we just pop and carry on with the day. Okay, so let's try this out. I will pop -3, and then you'll see the stack will only contain -2 as our current item, and then I would run the pop twice to remove 0 as well, but -2 will remain. You can see. So I'll pop again, and then -2 will still be there, so -2 remains our item in the array. But when I pop, finally our array will become empty. So here, this is a second solution aside the other one, and a much simpler one than the first. So I'll just, this is easy to understand. I mean, this is also easy to understand, but this is easier. So I'm just going to do this. I just go all the way here, put this here, and then run this code. This should work 100%. So confident. Yeah, it worked. And then we can run this code. We can submit this as well. And oh, okay. This index out of range. Okay, so I know what's happening here. Get mean, right? What's going on? Okay, so we also, when we are doing something like this, we need to respect, I mean, we need to put into consideration, I need to put into consideration the fact that the array might be empty and only run some operations when the array is not, just edge cases. So here, return self mean -1, list index out of range. Well, the only case where that will happen is when we don't have an item in the range. So return this if mean if self, that's mean else we want to return an empty array, right? And then we also want to pop, yeah, I think this can save us. Oh god, no way. This can save some time. mm, yeah, top of the stack as well. I mean, we are, yeah, this is not an issue. It's just mean, right? It's just mean. And let's run this again before we submit. Yeah. Yeah. Oh, runtime error. What's going on? It's not a value as expected return type. Okay. What do you want to return? This returns an integer. Hmm. Oh. Okay. The light is gone again. No bloody. Oh, I am suffering. Christ. I am. My monitor is connected to, unless I unless I use a single screen for my work, then I won't be able to see what's going on the monitor screens. The monitor screens are connected to that. I'm actually surprised my camera is still on, because currently I can't see anything on my screen. I can only see my other screen here. So there was an error, and apparently we can't, for empty list it will throw an error. Yes, that's true. From lazy YouTuber. Yeah. This is interesting. And I don't know when they are going to bring back the lights. So let me just try and move everything to my. Oh, the light is back. This is this is terrible, honestly. Struggling for lights, struggling for everything. Literally, it's bad. It is very, very bad. So let me bring back this. Um, I'll just use this here. Properties, easy camera. Okay, okay, right. The network is back again. Uh, this is the worst experience ever. Yeah. So I think the reason why so they did push push, right? Push push push. That's three. That's three. Get minimum. Hmm. Why is get pop 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 get min? Oh, wow. This is interesting. So, uh, are they? Nah, there is no way. This is a null value. There's nothing in this array here. When you get min first time, it means it's supposed to be zero. I don't know why it's one. This empty string here doesn't actually work. I'll keep this here, right? And I will push in my implementation. I'll push the empty array. So I'll just do this and see what's gonna happen, right? Push, it was like this. Oh, why? It's supposed to be an integer, right? Push, yeah, integer. So why didn't this work? It says last index mean is out of range, meaning there was no value there. Hmm. This doesn't make sense to me. Let me look at the editorial. Oh god, it's locked. Who solved this question? Solution. Easy mind diagram. Let me look at two solutions first and see what they did differently. It can't possibly be. So here's what he did. Setting means stack to what is the value? Okay, so the value is here. Means stack. If there's an item in means stack, then do value like this, like that. Mm, the only thing this minimum value does is to keep a certain, so regardless of what the comparison output is here, we still want to add that value to the minimum stack, which actually doesn't click in my head yet, because I only want to add an item. Except in this case here, where we always want, if we want to pop at the same time we are removing an item from the stack, then this is valid. Then we just, in that case, that's the only thing that will make sense to me. Otherwise, I don't think so. I don't think this makes any sense at all. So here we want to pop each time, and here we can only add values that are, every in each iteration we want to know the, I mean, obvious. So every time we push an item onto the stack, we want to know at that point in time what item is the minimum, right? And then we still need to add it on top. Uh, well, in that case, it makes sense, but also this, my previous implementation made sense, but I don't understand why that error was coming up, right? But let me just do it that way. So here, I can only add items to the stack each time, right? Well, I want to add which one. So here, value, I can do this, value is equal to self domain. So we always want to append the value to the stack as well, right? But then we want to only append the minimum value. Okay, so if there's an item in the stack, so here's what I'm going to do. It's quite it's quite you know understandable, but also value is equal to, so this here is still the same value, right? No matter what. So it's still the same value here, but we are just reassigning it a new value. So if minimum of self, the last item in the stack, self dot stack, no, self domain, sorry, self domain, and then we take the last item from the minimum stack, right? And then we find it against the other value. Yeah, so this is all you need to do. Then we append the minimum here, we get the minimum there, here and there. This works. I'm still not happy with this at all. Oh, the previous implementation was 93%. So let's use the the previous implementation had this minimum stuff here. So I can just remove this here. Oh, self min dot pop. I just want to pop like that, and then here we don't want to do it this way, right? We don't want to do it this way. We want to always append the recent minimum. So value should be equal to min, right, of the value here, right? if stack so sorry, return stack dot stack the last item. What am I doing? Self dot min self dot minimum the last item at the top of the minimum if there is an item in the stack, in the minimum stack. Self dot min else use the value. Then we just append self dot minimum and then add self dot min dot append the value. Right, so let's run this again. Let's submit this. Yeah, this is okay. Better. Let me solve another question. This is somebody else's implementation. Yeah, let's say stack has 5 elements, stack this has 3 elements, and you decide to exactly this is what. Yeah, I think your pop method only pops elements out of the stack when the stack. This is correct, right? This works, right? This solution works, but it was just similar to what I was saying before, right? But then what we actually are not, what I was not noticing is that every time we add an item to our main stack, right? The minimum stack gets updated, but just with the current minimum value. Yeah, it actually works. It works. It works. Which is this question. Can I reply a comment? Okay. So let me first of all verify what he's doing. If not, so self append, we are appending to the stack. Now, if not, if there's no item in the stack, right, in the minimum stack, or if the current value is less than the topmost item in the stack, then we only want to append. Oh well, this in this case this is wrong, right? Let me see how it's removing from the stack. So pop, yes, this is exactly what I did before. It works, but it doesn't work in certain cases, which is shocking. Well, that is one medium question cleared on LeetCode. Yep, check the medium, check mark. All right, let's solve another medium. I hope this is just stack. Greedy, what's greedy? Greedy algorithm. I don't know what greedy is, but let me see if I can solve the question. So check if a parenthesis string can be valid. So a parenthesis string is a non-empty string consisting of an opening parenthesis and a closing parenthesis. It is valid if any of the following conditions are true. If it is like this, it is valid. It can be written as, wait, hold on. It can be written as AB, right? A concatenated with B where A and B are valid parentheses strings. Okay. Okay. It can be written as A, where A is a valid parenthesis strings, parenthesis string. You are given a parenthesis string S and a string locked, both of length n. Locked is a binary string consisting of only zeros and ones. For each index I of locked, if locked at I is 1, you cannot change S at I. But if S at I is, if locked at I is 0, you can change S at I to either this and that or that. Return true if you can make S a valid parenthesis string, otherwise return false. So S will be this. Now if locked at I is 0, you can change the value of locked at I, otherwise if it is 1, then you can't change it. So here we can change it to an opening parenthesis, and this will match that. This matches this, but here, so let's go 1 2, we don't change this. We can change this to something like this. We can change, but if we, this is already valid, right? So from here to here is okay. We can change this if we want. It can change. It can change means, at your own will, not that it has to be changed. Okay, I see. We cannot change S or S3. Yeah, because the value at, this is 1 0, so here 0 1 2 and 3. So we can only change these two, but we can't change the other ones. We can't change this one and this, but we can change this, and that. This is also true. This is false, and it is locked. Locked is 0. Well. I think what's the constraint here? So S. Okay, so both S and locked are going to have the same item in the string, right? So it means we are not going to, we can use the length of 1, and we'll still be able to access item at those indexes, right? But we can only make changes based on certain conditions in locked, right? We can only make changes when locked is 0, but when locked is 1, we can't make changes. So how do we achieve something like this? Well, let me try and see. is an opening parenthesis. So it means um hmm. So we always want to have parentheses that match each other, right? Mm, mm. So let me come here. I'll just use this like this. I'll put the question here, and I will just copy a string, right? Like this. Come here, remove this, put this here, and do this. Let me increase my time for the stream. Okay, I still have 36 minutes. That's okay. So the question is, um, you know, let me just close this there. So we want to return true or false, right? If a string is actually um, has valid parentheses, and when the parenthesis is valid, right, it means the opening and closing are next to each other, right? Next to each other like this, or even something like this is still valid. This and that is valid as well. I'll just put here and then here. Something like this too is still valid. Three, three, valid parenthesis. Mm, but this time around, we want to, you know, um, change the direction, right? Um, even when a string starts with a closing parenthesis, right? Something like this. When we before we even switch it to something like this, we need to look at the value here. When it's 0, then it means we can flip, right? We can flip this, but then we can't flip the next one here because the value here is not 0, it's 1. So that cannot happen. This cannot happen. um I'm thinking of like possible cases we might have. um so first of all, why is this valid, right? What makes this string s a uh, valid in this case? So let me just remove this. I'll just come here and remove that like that. Okay. Yeah. So when we are here, right? When I here is equal to 0, I mean when the first element here, I will be 0, but it doesn't mean that it is the value here. So here I 0 and locked, the value of locked let me use first. So the first item in this string is 0, right? And then here we have a closing parenthesis, right? It means we can either keep it this way or we can change it, right? Now, what will prompt us to change the direction of a parenthesis? Well, we can start a string with a closing parenthesis, right? We can start a string with a closing parenthesis. We always want an opening before closing. So, condition 1, if it is closing, right, then we want to open it, so we'll switch this to that, right? But how do we switch? We just switch it to the opposite one. We are not doing for other items, otherwise I would have had like a curly brace and a match, blah blah blah, all of that, but we don't need that here. We don't need a map here per se. um Well, we might need just like one map. I'll just put something like this here, just to look up the next value. So here's what I'm going to do, right? Whenever I see a closing parenthesis like this, right? I want to create a stack. Okay, so I add it to the stack like that. No worries. I add it to the stack. Let me just go here. I'll just check. I'll do this to this. Yeah. So when I add this to the stack, I need to find, when I'm at this point, right here, I can't make a change, right? Hold on. In the cases where I don't make changes, what do I do? I just keep the item like that. Well, hold on. This is a bit confusing. What when we are at 0, right? When the value is 0, the value of locked is 0. It means we can make a change, right? We can change the direction of the parenthesis. That doesn't necessarily mean that we need to change the direction. It just means that we can if we want to, if we wanted to. I mean, um, so when we see something like this, right, it means, you know, when the next one is like this, then this is not, this needs to be changed to match this. This needs to be changed to match this, and we can then cross them off as a match. Mm, 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 mm. I'm still thinking, because we can't keep adding the opening parentheses into a stack. Well, technically we can, right? But we can only do that Oh, okay. So let's say here, right? We begin to add the first item we see into the stack because we want consecutive elements to be equal, right? I mean to match, to form a valid parenthesis. So I'll just do it this way. I'll do it like this. And then the next item I want to look at is this one here. If this one is equal to this the one on top of the stack, right, and the value here is 0, right, the previous value is 0, then it means we can change this, right? We can change this to this. We can, let me just do it this way. We can change this to this and pair it up with this one before removing it from the stack. So we'll pair it up with this one here, which is like this, and then we remove this from the stack, right? Then the next item will be this. The value here is 0, so we add this to the stack regardless, right? The next item, will be, I might even need to have two stacks, right? I might even need to have two stacks. One that checks for, you know, a change, if we can make a change, right? So here I add this item to the stack. This a C, I mean an opening parenthesis. The next item I have is a closing parenthesis, right? But I can still look the value of this one in the locked string. If it's locked, then we can't make the change. I mean, if it's 1, we can make the change. If it's 0, we can make a change when this and that is not valid. So here we can see that there is a match, right? There's a match here. But there's one missing piece, right? What are the conditions that we need to check for in order for us to know when to make a change? If we had a map like this against this, right, and we look into our map, right, we look inside our map. So yeah, when we look into our map and the value of this here is inside the string, then we know we don't need to make a change, right? But if the closing parenthesis is not the same as this, when we have this, then we need to change it to this and then cross it off. Then we are here. We add this to the stack still, right? We add it to the stack like this, and then we check for the next one, which is 0, right? We also add this to a different stack here. Then you can see the next item here is a closing parenthesis, right? It's a closing parenthesis. Okay. When it's a closing parenthesis, what do? We want to check the corresponding value. The corresponding value for this closing parenthesis is the opening parenthesis. But already we have also an opening here. But if the value of this is 0, right, I'll just call this the locked pointer. So if this is 0, it means we can change it to this, right? We can change it to this, and then if they match, we cross, we remove from the stack. But what if we had something like this? I'll just do it this way. Or what if we had like, you know, this was not like this, but like this? What if we had this like this? It was going this way instead. What if it was like this instead? What happens in this case? Well, the next item we are looking at, right, will surely have like a pointer here. If the next item is not, hmm, we only want to have one item at a time in the stack, right? So there will be no need, there won't be any need for that check. Because in a case like this, right, here we have locked that is 0, which means we can change this to something like this, right? But already we have an item in the stack. We have an item in the stack. This will be in the stack at this point. So we only want to have one item in the stack at all times. So when we change this to an opening stack, a closing parenthesis, sorry, then we can compare the value here. The value in this stack here. If it's not valid, then okay. So let me go back and explain again. I think I kind of get it now. Well, let's see. Yeah, that made sense to me, but let me see if it actually makes sense at all. So I'll have two stacks, right? And the point is, I just want to make sure that there's only one item in the stack at all times. So here's what I'm going to do. I'm going to take the first here, this one here, and I'm going to add it to the stack. So here's my stack, right? So here I add this to the stack, no problem, right? Although I need to also keep track of this one, so I create a second stack here and add this to it. So this is 0, right? This means the first item here can be changed, right? This is just a pointer. Okay, now this next item I see here is 1, right? 1 is there, so add stack yet. I don't want to add this item here. I don't want to add it to the stack at all, not even yet. I don't want to add it to the stack. I just want to compare it with this one and see if I can form a valid parenthesis from this here. So what I need to do is I need to look at, what value this corresponds to, right? Now when I look at this, right, this matches something like this. Okay, but what is the value of this? This is still a closing parenthesis, but this closing parenthesis matches an opening parenthesis, but the value we have in our stack is a closing parenthesis. So what do? I would then convert it based on the value that I have in our green stack here. I'll convert it to something like this. I'll convert it back to a C, right? I'll convert it back to a C. Then, this would then match this, right? This would then match this, and then I will now pop this from the stack. So I'll remove this from the stack again. Let me just remove that. I'll come here. So I'll remove the C from the stack like this and remove this as well from the stack. So nothing is there anymore. So here is where I'll be next. So So I'll just put this here, and then what's the value here? This is 0, right? I'll first check the second one, this here. Now what's the value of this? And is there any item in the stack? Yes, there's an item in the stack. So what's the corresponding value for this? It is this. So what is this value here? It is 6, so it matches. So we cross that off and we remove this as well. In this case, we don't need to transform, even though we could, right? But we didn't need to do that because this already matches this. So then we look at the next item, we add it to the stack, we add, where am I? So I've already passed here and here, so I'm here. Oh my god. Oh, oh, lights. Light is back. Light is back again. I'm so disappointed. Oh my god. My stream shouldn't end. Oh Jesus. Please, please don't end this stream. I beg you. Don't end this stream. Do not end this stream. Please don't remove my stream. I am begging. I am begging. Oh God. Yeah. I mean, you can say that. Right. Where was I? I don't even know where I was. Okay, so we are looking at this. So the flow is we add one item to the stack at each time, right? And look at the corresponding locked binary value. When it's 0, it means we can, change the direction. Otherwise, we just leave it. But when it's 1, it means we totally can't. And yeah, so I think that's like the most important things to note. And I'll go ahead and implement this now. So let's see how we implement this. So okay, um I'll do it here. Remove. What's this? Where's the question? Oh, it's here. I'm not going to do it here. I'll just do it in my code editor. Check if parentheses string can be valid. I'll just call this can be valid parentheses. Oh no 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 no. So let me just go through step by step. So the first step is to have um, our stack for, I'll call this S stack or stack. Alright, stack S is equal to an empty array. Then I'll have locked lo, okay, I'll just call this binary stack bin stack. So bin stack here like this is also equal to an empty array. And then I will loop through the string. Oh my god, no no, please don't end the string, please don't end it, I'm suffering. Wait, is it working? Is this working? It's not working yet. My internet is not working. Please let me give like 5 minutes. Oh fuck. Oh no no. Please no. Please. 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 I want to take a bold step and switch my network. Otherwise, this will not work like this. I can't continue like this. Network is not stable yet. Well, this is painful. Anyways, so I have two stacks and it says excellent connection. That is strange, but honestly, I'm struggling with my network. It's so embarrassing, but hey, let's go ahead and implement this bad boy. So I always want to look at. So here's what I have. Let me just pull this back. When I get a first value, I want to, add it to the stack. So for for I in range, right? Range the Christ, what am I doing? Range of so I want to start from 0, right? So 0 all the way to the length of, we can choose either s or locked, right? S or locked. Okay. So if not um being stuck and stacks 2 is also empty, right? Stack s. This is a weird name. I can just say s stack like this. This will work. I'll just say string s stack. Now, you know what? Let's just leave it like this. So if there's nothing in those stack, well, or let me start with an item in it, right? So if this and that, meaning else, we can just do bin stack dot append locked at I, and then s stack dot append s at I as well. So, but in the case where there is an item in this stack, so what do we want to do? Well, first of all, I need to check if the stack is if bin stack, right, the last item in the stack at 1, if this is equal to, if it's equal to, so yeah, I'll just create a simple map. I'll just call this map map of p, or map brackets. I'll just call it map brackets, or brackets map, brackets map. The reason why I want to create this is brackets map. The reason why I want to create this is to have like an accurate way of checking, if we have a closing parenthesis or an opening. So if it's a closing, sorry, if the item we're looking at is in this bracket map here, if it's inside bracket map, because bracket map we have only one. So if it's a closing parenthesis, right, and in our binary stack too, I'll just come here. I think it's time now to switch my network. And in our beanstalk here, we also have, and beanstalk, the last one is equal to 0, right? So we want to know if we're using parenthesis and this is, you know, that, right? If it is, then we want to do this. We want to convert it with this one here. We want to convert it to this here, right? So again,